Hello everybody, myself Nalinikan Jana, Senior Lecturer in Physics, Bharuneswar Mahavidyalaya, Utkal University. Our today's topic is torque, and after that we will go to discuss about the conservation of angular momentum of a system of particles. The conservation of angular momentum of a system of particles. So, let us start with torque. What is torque? In my previous class, I have just given a very brief idea regarding torque. Let us discuss what is torque. In linear motion, we know force, and here torque is the counterpart of force in rotational motion. That means, torque plays the same role in rotational motion as played by force in linear motion. Then what is torque and how it is related with force? Torque is the rotational effect of a force. That is, torque is the turning effect of force. Also, torque can be defined as the moment of force, and in the similar way as F is equal to ma, that is the product of mass and linear acceleration, your torque can also be expressed as the product of the moment of inertia and the angular acceleration of the body. Okay. Let us start with what is torque. The first one is torque is the rotational effect of force. Number 2, also torque is the moment of force. Hence, we can also write torque plays the same role in rotational motion as played by mass in linear motion. Number 4, we can express torque as the product of the moment of inertia and the angular acceleration of the body, because we know force is the product of mass and acceleration. So, torque is the product of moment of inertia and the angular acceleration of the body. That is, torque is equal to tau is equal to I alpha. Also, we have known that a tau vector is equal to r vector cross f vector. That is, torque is the cross product of the perpendicular distance of the particle from the axis of rotation and the force acting on the particle. Hence, we can further write as number 5 as torque is the cross product of the perpendicular distance. Torque is the cross product of the perpendicular distance of the particle from the axis of rotation and the force acting on the particle. That is, mathematically we can express torque in terms of force as. Now, mathematically we can express torque in terms of force as tau vector is equal to r vector cross f vector, which is equal to r f sin theta n cap, implies as tau is equal to r f sin theta, where theta is the angle between the directions of r vector and p vector, where theta is equal to angle between r vector and f vector. Now, since torque depends on theta, hence torque varies with the variation of theta, that is with the variations of the directions between force and the r vector. Special cases: number 1, if theta is equal to 0 degree or 180 degree, then sin theta it will be equal to 0, and hence tau is equal to rf sin theta will be equal to 0. That means, when the force acts parallel to the perpendicular distance, then no torque acts on the body. Number 2, if theta is equal to 90 degree, then sin theta is equal to sin 90 degree is equal to 1. So, tau is equal to rf sin theta, which is equal to rf. Tau is equal to rf, and this is equal to maximum value of torque. So, torque will be maximum when the radius vector or the perpendicular distance is perpendicular to the force acting on the body. Now, from this expression we can conclude that for a particular body in rotational motion, torque is constant. That means, for a body in rotational motion, torque is constant. That is, tau is equal to r f is equal to constant, which implies f proportional to 1 by r. That means, for a body in rotation, the force varies inversely with the perpendicular distance of the particle from the axis of rotation. That means, if R increases, then F will decrease. That is why the force acting on a body will be minimum if the perpendicular distance of the particle is maximum from the axis of rotation. Let us take the example of opening a door. While we open a door, we apply a force at the edge of the door. Why we apply the force at the edge? Because to open a door, torque is required, and a torque is independent of a position about which the moment is taken. But in case of the door, the axis of rotation is at the point where the hinges are connected to the door, and when we give a tangential force to the door, then the door starts rotating about the axis where the hinges are connected. Now, as torque is independent of the position about the moment is taken, hence Rf is equal to constant, and hence F proportional to 1 by R, where we can conclude that with the increase in R, force decreases, and as we give the force to the door at the edge, its distance becomes maximum, and hence a less force is applied to open the door or to close the door. And that is why the handles are connected at the edges of the doors, not at the middle or even not at the points where the hinges are connected, because in those two cases the distance between the axis of rotation and the point of application of force will decrease, causing a greater force to require to open or to close the door. Now, let us have the important terms or important notes connected with torque. Number 1, torque is an axial vector. Because it is associated with the axis of rotation, and since it is a vector quantity, then what is about its direction? We know tau vector is equal to R vector cross F vector. Tau vector is equal to R vector cross F vector. That means cross product of two vectors, and we know in case of cross product of two vectors, the vector which is the cross product of other two has the direction perpendicular to the plane containing these two vectors according to the right hand screw rule. That is why the direction of torque will be along the axis of rotation according to the right hand screw rule, whether it is clockwise or anti-clockwise. Then the dimensional formula for torque is m1 L2 T minus 2, and similarly the units for writing torque, units of torque can be expressed as gram centimeter square second minus 2 in CGS system, B kg meter square second minus 2 in MKS or SI units, and see it is pound foot square second minus 2 in FPS system. Though work and torque have the same formula, that means work is the product of a force and a distance, and a torque is also the product of force and distance. Hence, both the quantities have same SI unit, Newton into meter. Here is also Newton into meter, but joule is a specially assigned SI unit of work and energy, and hence it cannot be applied to the unit of torque in SI. But we can write the SI units of work and torque as a Newton into meter, and also for torque we can also write the SI unit as Newton into meter, but we cannot write the SI unit as joule in case of torque, because it is a specially assigned unit, SI unit for work and energy. The direction of torque, as we have discussed, is always perpendicular to the plane containing R vector and F vector according to the right hand screw rule, that is, it is always along the axis of rotation according to the right hand screw rule. And this torque is also known as the moment of couple, and torque is the cause of rotational motion, because in linear motion, in Newton's second law of motion, we know that force is equal to mass into acceleration, and from first law of Newton in linear motion we know that force is the cause of linear motion, as torque is the counterpart of force in rotational motion, and torque plays the same role in rotational motion as played by force in linear motion. Hence, torque is the cause of rotational motion, as force is the cause of linear motion. So, it is all about our torque. Then we will go to discuss about the law of conservation of linear momentum of a system of particles. Last sentence टा टिके काटी देवे. Law of conservation of angular momentum. Already we have discussed angular momentum, and in discussing that we came to know that angular momentum is the amount of rotational motion possessed by the body, and from the mathematical expression for angular momentum we know that L vector angular momentum is equal to the cross product of R vector cross P vector. Here we have to discuss the law of conservation of angular momentum. Generally, the questions are asked in the exams like state the law of conservation of angular momentum and prove that the law of conservation of angular momentum of a system of particles is always constant. So, the question is generally asked like this: state and prove the law of conservation of angular momentum of a system of particles. The question is generally asked like this: state and prove the law of conservation of angular momentum of a system of particles. So, in solving this question we should first give the statement. As we know, in case of the law of conservation of linear momentum, that the total linear momentum of a system of particles is always remains same. That is, the total linear momentum is constant for an isolated system. Now, in case of angular momentum, the law can be stated as the total angular momentum of an isolated system always remains same. That means, the total angular momentum of an isolated system is constant. So, we can write the law as the law states that the total angular momentum, of an isolated system always remains same. That is, for isolated system angular momentum is equal to constant. Now, we have to prove this. So, the statement is like this: the law states that the total angular momentum of an isolated system always remains same. That means, for isolated system, angular momentum is equal to constant. And to prove this, what we have to do? Let us consider a system of particles. Let that system consists of extremely large number of particles, and let us consider only the ith particle of the system. Now, if with respect to an arbitrarily chosen origin, Ri vector is the position vector of the ith particle and a Pi vector is the momentum of the ith particle, then the angular momentum of the ith particle can be expressed as the cross product of Ri vector cross Pi vector, which we have discussed in our previous class. So, let us first consider the ith particle of a system. Our duty is to state and prove the law of conservation of angular momentum, for which we have already stated the law of conservation of angular momentum. And now, to prove the law of conservation of angular momentum, let us consider a system of particles from which we can consider the ith particle of the system. Now, let us consider the ith particle of the system. If Ri vector is equal to position vector of the ith particle and Pi vector is equal to Mi Vi vector is equal to momentum, linear momentum of the ith particle, then angular momentum is equal to L I is equal to R I cross P I, and this is the angular momentum of the ith particle. So, the total angular momentum of the system of particles will be total angular momentum of the system will be equal to L vector, which is equal to sum over I L I vector, which is equal to sum over I is equal to 1 to n R I cross P I vector. Let this is termed as equation 1. Now, let us differentiate this equation with respect to time. Now, let us differentiate this equation 1 with respect to time. So, we can write equation 1 as dl by dt, which is equal to d by dt of sum over I R I cross P I, and this can be expanded into as sum over I is equal to 1 to n R I cross d P I by dt plus sum over I is equal to 1 to n d R I by dt cross P I. But we know that dp by dt is force and dpi by dt is the force acting on the ith particle, and dri by dt is nothing but the velocity of the ith particle. So, this becomes as sum over I is equal to 1 to n Ri cross Fi plus sum over I is equal to 1 to n Vi cross Pi. But the momentum of the ith particle is equal to the product of its mass and its velocity, that is mass of the ith particle and the velocity of the ith particle. So, this can be written as sum over I is equal to 1 to n Ri cross Fi plus summation I is equal to 1 to n Vi cross Mi Vi. Now, this becomes as V vector cross V vector, but from the properties of cross product we know that if a vector is crossed with itself, then the result is a null vector. That is why V cross V will yield 0, and hence this term will vanish, and now our dl by dt will become as sum over I is equal to 1 to n Ri cross Fi. That means now dl by dt will be equal to sum over I is equal to 1 to n Ri cross Fi. Let us take this as equation 2. But in case of a system of particles, the net force on a particle is equal to the sum of the external force acting on the particle and also the sum of the internal forces acting on the particle. That means, if we consider the case of ith particle, then the total force acting on the ith particle will be equal to the sum of the external force and the sum of the internal forces acting on the particle. That means, we can write now Fi as Fi external plus sum over j Fij, where this Fie stands for the external force acting on the ith particle, and the sum of Fij is the sum of the internal forces acting on the ith particle, and here Fi represents the total force on the ith particle. Hence, we can write this equation 2 as in terms of this, as now our dl by dt will become as sum over I is equal to 1 to n Ri vector cross, in place of Fi we can write Fi external plus sum over j Fij, and on expanding this we can write sum over I is equal to 1 to n Ri cross Fi external plus sum over I is equal to 1 to n sum over j is equal to 1 to n Ri cross Fij. But we know that the sum of the internal forces acting on a body is always 0. That is why this term vanishes, and hence our dl by dt will become as dl by dt will become as sum over I is equal to 1 to n Ri cross Fi external, because this term vanishes as the sum of all the internal forces acting on a particle is always 0. Here we have arrived at the term dl by dt is equal to Ri cross Fi external, but we know that the torque acting on a particle is the cross product of r vector and f vector. Hence, for the ith particle, the external torque acting on it will be equal to the cross product of the r vector and the external forces acting on the ith particle, that is what tau on the ith particle external torque will be equal to sum over I Ri cross Fi external. Let this is termed as equation 5. Now, comparing equations 4 and 5, we can write our dl by dt is equal to tau external. That means the time rate of change of angular momentum is equal to the external torque acting on the particle or the system. But our actual aim is to prove the law of conservation of angular momentum, which is stated as for isolated system total angular momentum always remains same. But here what we have shown? Here we have shown that the time rate of change of angular momentum is equal to the external torque acting on the system. Now, we have to consider the case of isolated system, but for isolated system the total external torque acting is 0, that is tau vector external is equal to 0. So, this equation now can be written as dl by dt will be equal to 0, which implies that L vector is equal to constant. That means the total angular momentum of a system of particles is conserved, and this proves the law of conservation of angular momentum of a system of particles. And this is also same for a single particle also. That means, for a particle the total angular momentum is conserved if the particle is isolated. And the law of a conservation of angular momentum is very much familiar with various practical cases which we observe in our daily life, like the cases of dancers, gymnasts, divers and skaters. How this law is applicable to all these cases? Let us have a brief discussion on these ideas. From the law of a conservation of angular momentum, we have seen that L vector is equal to constant. That means total angular momentum always remains same, and from this we can write L is equal to I omega, where I is the moment of inertia and omega is the angular velocity, and that is why we can write this L equal to I omega is equal to constant, implies I omega is equal to constant, implies omega proportional to 1 by I, omega proportional to 1 by I, where I is the moment of inertia of the particle. So, but I is equal to m r square. That means the moment of inertia can be expressed as the product of mass of the body and the perpendicular distance from the axis of rotation, and hence we can write this as, so omega will be proportional to 1 by m r square, which implies omega proportional to 1 by r square, because m represents the mass of the body which is constant. But also omega is equal to 2 pi by t. Hence, here we can write 2 pi by t proportional to 1 by r square, which implies t varies directly with the square of the radius. That means t proportional to r square. What we have written here are from the law of conservation of angular momentum. First of all, we came to know that angular velocity of a particle varies inversely with its moment of inertia, and angular momentum of the particle also varies inversely with the square of the distance, and also the time period of the particle in rotational motion varies directly with the square of its radius. And these situations can be applied to various practical cases, from which we came to know that the dancers, the gymnasts, the skaters and the divers are under the law of conservation of angular momentum. Let us discuss them one by one. In case of dancers, when we observe that a dancer is dancing with a very greater velocity and is rotating, then what she or he does? When he wants to move with a very greater velocity, that means when he or she wants to increase her angular velocity, that is omega, what she has to do? She has to reduce her radius. That means if she wants to increase her angular velocity, then she has to reduce her radius. And when during her rotation, if she wants to decrease her angular velocity, then what she has to do? She has to increase the radius. That is why when a dancer moves with a very greater speed, then he or she often closes her arms in such a manner that its radius decreases. As a result, its angular velocity increases. And when she wants to stop her rotation, stops dancing, then in that case what she has to do? She has to stretch her hands in such a manner that the radius increases. As a result, her angular velocity will decrease and she will comes to rest. And this situation can also be applied to gymnasts. And you must have seen in case of Olympic sports, the small girl childs, they perform the gymnast very well, because when they start gymnasm, what they do? They run with a very greater velocity and jump to the space and curl their body into a loop, because as they form a loop, the radius of their body decreases, causing an increase in angular velocity, for which they rotate with a greater speed in the space and form a number of loops in the space, which leads them to have greater points. And when they come to land from the space, then what they do? They stretch their body by increasing their radius to decrease their angular velocity, so that after performing the loops in the space, they stand with safe if they stretch their arms. And exactly this situation can be applied to divers. You must have seen the divers in cases of swimming pools. The divers make jumps, they dive into the swimming pool or into the river or into a pond full of water. But there are two types of divers. Some of the divers make their body very straight with their hands stretching upward to making a point. As they make their body very straight and they jump to the water, then they pierce into the water with a very greater velocity, causing less friction to act on them. But there are other divers. While they dive into the swimming pool or into the pond full of water, what they do? They jump into the space and immediately they curl their body into a small circular size or spherical size. As they curl their body, their radius becomes minimum, causing their angular velocity to be maximum, for which they make a number of loops in the space before they fall into the surface of water, and hence they make themselves to have more points by diving into the swimming pool by making number of loops in the space. And exactly this same situation or the law of conservation of angular momentum can also be applied to skaters. What do the skaters do on ice surfaces? The skaters have two sticks on their hands. When they move on the ice, they put the sticks on the ice and move forward. But when they want to turn, what they have to do? They normally stretch the hand in the opposite direction of they want to turn, because when they stretch their hands, the radius along that direction increases, causing a less angular velocity, so that the angular velocity on the other side becomes more, and hence they are able to turn on the ice surface. So, the law of conservation of angular momentum is applied to various cases, and there are other familiar and peculiar cases in our daily life. If we pick two leaves, one is of the banana leaf and the other one is the bamboo leaf. In case of banyan leaf, it is in a shape of like this with a greater breadth, but in case of a bamboo leaf, it is a very thin leaf, and when we drop both of them from a certain height, what happens? Due to its greater radius, this banyan leaf falls exactly in the straight path with a smaller velocity, with a greater velocity to the surface of the earth. But what happens to the case of bamboo leaf? When the leaf falls, because of its smaller radius, its angular velocity increases and the bamboo leaf falls by rotating a number of times in the space and finally falls to the ground. And this situation becomes only because of the law of conservation of angular momentum. Here we have stated and proved the law of conservation of angular momentum, and also we have discussed the various practical cases which often occur in our daily life where the law of conservation of angular momentum is applied. So, students, I feel you must have a better understanding regarding torque and the law of conservation of angular momentum. Okay, students, you must have a better understanding regarding torque and conservation of angular momentum. Now, with this, let us stop here and wish you many thanks